Okay, so before I start with the slides you guys have in front of you, I've got two slides just of review, which hopefully can help, in a visual sense, make sense of the two types of bonds we've talked about so far. Okay? Last day we talked about how to name ionic things and covalent things, and they each have a different naming scheme, and the reason why is that the way in which they bond is slightly different. One is more of a sharing of electrons, and another one is more of a transfer of electrons. I like this analogy, so I'll probably use it a lot. Imagine that I want to buy something that is $8. Okay? And I actually have $9, but somebody else only has $7. Well, if I have 9 and they have $7, I have $1 extra, and somebody else doesn't have a dollar they need, right? So what I could do is I could just give them one of my extra dollars, and then we both have 8. Does that make sense? What kind of bond is that? That's ionic. That is me being very generous and saying, hey, look, I have an extra electron right here. Hey, you need an electron. This works out great. Here, have my electron. Does that make sense?
That's ionic bond?
That's ionic. Okay. Ionic things form between metals and nonmetals. So if they're on opposite sides of the table, it'll form an ionic bond. That's one of the ways that things can get their 8 electrons. But there's another way things can get their electrons, and it's by sharing. Okay. For example, let's say that we want to buy something that's $8. But rather than me and my friend having 9 and 7, let's say I only have $5 and my friend only has 3. Neither of us have what we need, do we? But if we pool our resources and collectively share them, 5 plus 3 does equal 8. But it's different, isn't it? In the first scenario with 7 and 9, we both get to the number 8. Does that make sense? Because I go up 1, they go down 1, we both get to 8. But in a second scenario where I have 5 and someone else has 3, are we able to buy 2 different things? Well, no, we can only buy 1 thing. Of course, we still bought something though, right? We have to share. And that's kind of what happens in a covalent bond, is sometimes rather than the electrons, literally this guy loses his electron and is given away, they'll actually sometimes we'll draw them as like shared. They're pooled together. Here's one more diagram I have. Covalent things will often have, like, say here, this guy has an electron, this guy has an electron, and now they're kind of drawn in the middle of the two, where they're both joining up. They're sharing their electrons. The other type is the complete transfer. You have an electron, and you're just, I'm going to give it away. Here, you have it. I don't want it. Does that make sense so far?
Yeah.
Okay. Well, my goal now is to build to deeper levels. To be honest, what we've covered so far is really only a fraction of all of the compounds that we've learned about. There's actually many, many more chemical compounds that we need to learn how to name. And so to do that, I've kind of drawn a bit of a tree here that I hope will help keep track of the different naming schemes we have. I think there's actually 4 naming schemes you need to know. Okay. The first one, over to this side right here, we've already done. Molecular covalent things. If something shares electrons, we always use dis and tris. We've already kind of worked on that one. The other possibility is the ionic. Ionic is like a transfer. Maybe you could call it like a give-take kind of relationship. I have an electron, you want one. Here, take it. And we've kind of covered this branch of the tree right here. We've covered things that are binary, things that only have 2 things in the formula. But like I just said a few minutes ago, there's more than that. Like, we're only just scratching the surface. And so today I want to talk to you about 2 other types of compound names that you might need to know. One of them, multivalent, and the other one, polyatomic. So one of the things you can tell multivalent things by right away is this symbol right there. Multivalents are characterized by using Roman numerals. Do you guys know Roman numerals? Did you cover those in previous years? Okay, maybe I should just go over that real quick just so you guys know. Using a Roman numeral system, 1 looks like this, like an I. I is 2. I is 3. Yeah, okay, so then skip 1. 5 is a V. So the way they figured out how to do 4 is it's 1 before 5. It's actually IV. So what this means is that we have 5, but we want 1 number before 5. So IV is 4. If you want to do 6, 6 looks like this. V, I. That means 1 after 5. 7 is VII. That means 2 after 5. 7. I'm running out of room here. 8 is VIII. That means 3 after 5. We don't use 4 though. We don't put four dots in a row. I don't know why they don't. But I'm going to jump ahead. 10 is X. Well, for 9 then, we use the same logic as with 5. So 9 is IX. That basically means 1 before 10. Out of curiosity, some of you guys know this, or is that new?
Yeah.
Okay. This is going to come up when we use one of our naming systems. So I'll get to that in a second. But you can tell when things are multivalent because there's going to be a Roman numeral in between the words. The other naming system I need to talk to you guys about today is something called a polyatomic. Okay. Atomic, atoms. Poly, more than one, many. Yeah, many is probably a good way of putting it here. I'm going to show you guys some compounds where, you know how binary means 2. Just calcium and just fluorine. Well, we're going to have some compounds where there's more than 2 things there. Like here there's a compound with an Na and an O and an H. There's 3 things there. It needs a different naming scheme. Or here, Li, N, and O. 3 things. Different naming scheme. This one's even more. N, H, C, and O. There's 4 things in that one. So it's going to require a different naming scheme. Does that make sense? So that's my goal today, to talk about how to name things under this branch and this branch. So I'm going to start with multivalent. Is this what you guys have in front of you? I feel like I lost a bullet right here. Is there something down here under the CR? Does it actually say that, or did I leave it blank on yours too?
No, blank.
Okay, good. I was wondering whether I left it. Okay. So here's multivalent. If you guys have your periodic tables in front of you, if you look on the extreme right and left-hand sides, usually things right over here have only 1 plus charge. Like this guy's usually +1, +2, +3. And if you look over here, often does it tell you, but usually these guys are zeros and -1s and -2s. But there are a lot of elements in the middle part of your periodic table where it lists more than 1 different charge there. Did you guys find iron? Like iron is number 26. On your periodic table, it should say 3 plus and 2 plus. Or if you go next to cobalt, 2 plus and 3 plus. Many of the transition elements, if you can read my first line here, they can form more than 1 ion. There are some things that apparently have the ability to lose 2 electrons, or to lose 3 electrons, or maybe to lose 4, or 5, or 6. Okay? And if you look at one of my big periodic tables, you'll discover that, like in an in-depth table, sometimes things have many charges. One of my favorite ones is manganese. If you guys can find manganese, it's number 25. What are the charges in your data books?
+2, +4.
+2, +4? Well, your data book only lists actually 2 charges, always. But if you look at this guy here, if you can see, it's actually, there's a 2, a 3, a 4, and a 7. So that means that somehow manganese can get rid of 2 electrons, or it can get rid of 3, or it can get rid of 4, or it can get rid of 7. And any of those are actually possible for manganese. Okay. What I need you guys to know about your data booklets then is that I'm only ever going to test you on the ones that are in your book. So even though the big periodic table might actually have more charges listed, we only worry about the ones that are in your book. Okay. The other thing I need you to know about your data booklet is that the one that's listed first is most common. So that one more time. Whichever one in your data booklet is listed first is more common. And maybe that helps to explain why some of them, they go like, say, the +3, and then they go the +2. And then other ones list the +2 before the +3. So although your data booklet has many of the charges listed, there's a couple of problems. It doesn't list all of them, because it might be missing a few charges that actually exist that are on the big table. And secondly, it lists them in order of how frequently you find them. Does that make sense? Okay, this causes a problem. Let's say we wanted to form a compound with chromium. Well, we'd have to ask ourselves, is chromium using its 2 plus charge, or is it using its 3 plus charge? Because it could be either. And so we need a way of naming these. So maybe I'll go to this question here. What will we call Cr2s3? So here's how I might try to solve this problem. You know how CrS3, what is the charge of sulfur typically? -2. Okay. Well, looking at that, how many total negatives do we have? We have 3 sulfurs. Each of them are -2. That makes sense that you have -6 total. Well, that means that we better have 6 chromiums total, positive. But they come in 2s. So is this going to be a +2 that I write up here, or a +3? +3. Because 3 times 2 will give me 6. But let's say that I had tried writing the +2 right here. +2 times 2 would only give me... Are those two things equal to each other? No, they're not. So here's the point I want to make then. There is a difference between using the chromium 2 ion and the chromium 3 ion. So when we write out this guy's name, we would call it chromium sulfide. But in between the two words, in Roman numerals, we tell you what charge of chromium it was. Because it could have been either the 2 or the 3. So we just said it was the 3. So we write in Roman numeral 3 in brackets. This would be chromium 3 sulfide. So I have a logical question then. What would chromium 2 sulfide look like then? Okay, well, here's chromium. Here's sulfur. I'm not going to go up to the board. I'll just do this from here. Sulfur's charge is -2. If we're using the chromium 2 charge, do these things fit together? Yeah. Perfectly. So actually, chromium 2 sulfide is just that. That is chromium 2 sulfide, and this guy right here is chromium 3 sulfide. The only difference, and it is very subtle, is that Roman numeral in the middle. Is this compound here, though, the same as that one? No. In fact, they're actually often very different. Sometimes this compound could be a liquid that's blue, and this compound here could be a gas that's brown. And the only difference between the two words, one is chromium 3 sulfide, one is chromium 2 sulfide. Does that make sense? So those guys are really tricky because you've got to watch out for those Roman numerals. As a general rule of thumb, the ones that have more than one charge are in the middle section of your periodic table. You guys remember what we called these guys right here in the middle? Actually, it says it right up there. These guys are called the transition elements, and they have a very different chemistry than everything else. Often when we count valence electrons, we actually kind of ignore these guys. Like, for example, bromine. We would actually say that bromine has 1, 2, 3, 4, 5, 6, 7 valence electrons. So if you get a Roman numeral, it probably means that you're working with somebody in here. Okay, why don't I do a couple examples just to make sure we got that? Let me just pick a few more. Let's try to name these compounds. So I'll just maybe write this in the margin here. Let's do CuCl. Let's use NiBr2. And let's do ZNO. Let's try naming these 3 things. We'll do it as a group. So CuCl. What does Cu stand for? Copper, sure. And what does Cl stand for? Sure, so we change it to chloride. But here's a question you're always going to want to ask yourself now. Does copper have more than one charge? Yeah. It does. What are the 2 possible charges for copper on your table? Don't worry about the big one.
2 plus and 1 plus.
Okay, so 2 plus and 1 plus. So look, if there's 1 chlorine and 1 copper, we got to figure out whether this was the 2 plus copper charge that we used or the 1 plus copper charge that we used. To figure that out, we better know what chlorine's charge is. Yeah, chlorine's charge is -1. So if there was 1 of each of them, this must have been a 1 copper. So I write it like this: copper 1 chloride. That 1 there is super important. If you forget to put that 1 there, It means we don't know which version of copper chloride we're using. And like I said, they can be very different from each other. Let's try the next one. Ni is nickel. Br, bromine. So we make it bromide. Now we gotta double check real quick. Does nickel have more than one charge? What are the charges possible for nickel? +3 and +2? Okay. So I'm just gonna write out the two possibilities here. There's +3 and there's +2. What about bromine? What's bromine's charge? -1. So which one is the nickel we must have used if we need two bromines to make it work? Probably the 2 version. Does that make sense? Because if you have 2 -1s, then you better need 1 + 2. So this must be the nickel 2 bromide version. That's the only way it fits. Because you're going to need like a little 2 after that. We don't actually write that though. How do those do so far? Does that make sense? Okay. Being very tricky on the last one. Zn is zinc. O is oxygen, so that's oxide. This is not correct. You don't put zinc 2 oxide. Anybody know why? Nice. Can you say that louder one more time? Yeah, there's only one charge. Zinc is only ever +2. So if there only is one charge, don't put the Roman numeral there. Does that make sense? The Roman numerals are only for things that I call multivalent. They have more than one charge to them. So, I mean, after a while, you'll get used to it and go, oh yeah, chromium has more than one. Iron has more than one. Zinc, oh no, zinc only has one. Like after a while, you'll know. Okay? But make sure you double check because that Roman numeral is very important. Sound good? I have more practice examples later if we need them. Okay, the second category of things I want to work on are called the polyatomics. And I talked about this word earlier, poly meaning many, ions. Well, you guys know what ions are, right? There's 2 different types of ions. There's the cations. Cations are positive. Cats have positive. And there's anions. Okay. The long and short of it is that we've discovered that there are some groups of atoms that can clump together and collectively hold a charge. And here's a couple of good examples. NH4. You can have 1 nitrogen and 4 hydrogens, and collectively they can have a positive charge. Okay? Or OH negative. An oxygen and a hydrogen, they can group together and collectively have a negative charge. And so these things that we've discovered, we call them polyatomics, and they're at the very, very top of your table. Now, they're not in this table here, but you see how there's a big gap in the periodic table? Often, that gap will be filled in with like a chart. And you guys have that chart in your table where it lists a whole bunch of polyatomics. Can you guys find that chart? Basically, they all have their own names. You don't have to memorize them because the chart is right there for you, but I imagine that over time you will probably get to recognize them. Okay? The key to recognizing a polyatomic is that there is more than one thing there. Like for example, if I gave you NaBr, there's only 2 things there. But if I give you NaOH, see how there's now 3 things here? It means that something in this compound must be in that top chart. So can you find something in this compound that's in the top chart? Yeah, there is an OH thing sitting right here. And if you can find it in your chart, OH minus is called, I have it written up here actually, it's called hydroxide. So let me talk you through how to name polyatomics. Polyatomics create compounds the exact same way with one difference. Don't ever change the last word to "ide." You know how we always change the ending to IDE? Just don't do it. And that's how you name them. Literally take the first thing, write it as it is. Take the second thing, write it as it is. And just don't change any endings. So let me do some examples here. Here is MgSO4. I know this is polyatomic because there's more than 2 things there. There's an Mg, there's an S, and there's an O4. So what I need for you guys to be able to do then is figure out, well, is an MgS, is that a polyatomic in the top of your table? Or what about an SO4? Is that a polyatomic in the top of your table? And I don't have it nearby, but can you guys find where SO4 2 negative is in that top table there? Can you find it? Yeah, it's called sulfate. So to name this, it's very straightforward. You call it magnesium sulfate. Don't change any endings. Just call the first thing as you see it. Call the second thing as you see it. Ta-da. Why can't I change the 8 to I? Why can't I call it magnesium sulfide? Why is that not valid? Yeah, it's something else. Magnesium sulfide is Mg with just a single S. And that's not the same thing as an Mg and an S and 4 O's. So here's another one. Barium carbonate is BaCO3. So hopefully you guys can find a CO3 2- somewhere in that table there. CO3 2- is known as carbonate. So why don't we practice naming some of these things here? I've got, what, 2 slides worth of them? 1, 2. Yeah, I got 2 slides. Why don't we do these ones together as a class? Just make sure that you guys have the hand. So, naming scheme. I'm going to suggest there's 4 things you need to know how to name. First, is it ionic or covalent? Then, if it is ionic, is it just a 2-part binary one? Is there more than one charge? Or is it polyatomic? So, like, I'm going to refer you guys back to this very first slide here. Where is it here? First, figure out, is it covalent or ionic? Then figure out if it is ionic, is it binary? Is there more than one charge? Or is it poly? So, is this ionic or covalent?
I missed out how you say poly.
What's that?
How do you figure out if
Is there a metal and a non-metal in this thing here? I guess in a way, yeah. Sodium is a plus. What about ClO4? Is that a thing you can find somewhere?
Yeah.
It's up in that top part of the table, right?
Can't really read it.
Yeah.
It's blurry.
Oh, that is kind of blurry. Okay, it's called a perchlorate. Here, I'll write it out for you. So to name this thing, you'd call it sodium, and then perchlorate. Sorry if that came out really blurry out of the photocopier. We don't change anything about it. If it's polyatomic, and I know it's polyatomic because there's 1, 2, 3 things here. Does that make sense how you name it? Like I said, it's kind of straightforward. Okay, this guy right here. Strontium is Sr. What did you say?
Sulfate.
Good, yeah, sulfate. If you can find this SO4 thing in your table, SO4 is called a sulfate. So we call it strontium sulfate, because SO4 is sulfate. Don't change it to sulfide, because sulfide is something different. Okay, what about this guy? What does Ca stand for? Good. NO3. You want to find it up in that table up there?
Nitrate.
Nitrate. Good. Okay, I got a quick question then. Why are there these brackets and a 2 afterwards? Anyone explain why that kind of exists? That's different. Because you need 2 of them. See, a calcium is a +2 charge. And the whole nitrate, all of it, the N, the O, the other O, and the other O, because really there's 3 O's there. There's 4 things together. All 4 of those things collectively have a -1 charge. So that means we need to have 2 of them. You got to be really careful with brackets. You don't want to write this then, CaNO3 2. Because you know what that implies? It implies 1 calcium, 1 nitrogen, and 32 oxygens. And that's not the same thing at all. So make sure whenever you're using a polyatomic, if you need more than 1 polyatomic, put the whole thing in a bracket. Because this is not the same thing. Okay. You know those rules I gave you about polyatomics? Okay, I kind of lied. There is one exception. And this is the exception. NH4 is the only one I've ever heard of. It's the only polyatomic on that whole list, which is positive. Positives are cations. Like if you guys look at that list there, every single one of them is negative. Except for one. The very first one was called ammonium. Second one? Sorry, second one then. I thought it was first alphabetically. So ammonium is a little bit different. it has to be listed first. So we're going to call it ammonium. And then you see how chlorine is second? This is my exception. You know how I told you you're not supposed to change the ending to IDE? We will on this one. This is the only time we will. So don't call this ammonium chlorine. Chlorine. Change it to ide. Okay. But never change the name of a polyatomic. Okay. This is the only one where you put the polyatomic first. Every other time the polyatomic is second. Okay, this last one is really mean. Anybody know what CR stands for? Good, chromium. Has anybody found what a CO3 is on that table yet? CO3. What'd you find? Good, carbonate is how you say it. Carbonate. Carbonate. Okay, here's the thing though. That's not its name. I've actually put two things together here. Chromium has more than one charge. You guys find chromium on the periodic table? How many charges does it have?
+3 and +2.
Yeah, chromium could be the +3 version or the +2 version. That means that I need a Roman numeral and a polyatomic. I can actually put those together. Okay. So to figure this out, what is carbonate's charge? 2 negative. Okay. So if we have one chromium and one carbonate, and the carbonate is a 2 negative, which one of these charges must we have used? The 2. Good, yeah, the 2, yeah. Because a 2 and a 2 would just fit perfectly together. So to answer this, it has to actually be chromium 2 carbonate. Be really careful. If something has more than one valence number on your table, it needs a Roman numeral. All right, and we'll do one more slide. This slide, now we're taking names, though, and going to formulas. So, calcium carbonate. So right off the bat, what's calcium? Ca. Good. Carbonate is CO3. Grab some. Is it okay? Do we just shove these things together? Actually, on this one we do, but let's talk through why. Calcium has a +2 charge. What was carbonate's charge? Yeah, like -2. I don't care whether you call it -2 or -2 negative. Like, I'm okay with either way of that, by the way. Do these things fit together? Yeah. So this is the formula, calcium carbonate. This guy down here I got to be careful on though. Beryllium is Be. Anybody remember what hydroxide was? Good, OH. On this guy right here though, I got to be careful because OH is a -1 charge. Anybody know what beryllium's charge is? +2. This means that they don't fit. So we're going to need more than one of the hydroxides. So I put a 2 there. Actually, that's wrong. I only said it a few minutes ago. Whenever you need to double up or triple up a polyatomic, make sure you put it in some brackets, yeah. Because what this means is that you want 1 beryllium, 1 oxygen, and 2 hydrogens. And what this means is that you want 1 beryllium and you want 2 of both the oxygen and the hydrogen. This little 2 right here applies to everything in the brackets. It means you have 2 of both. One thing you'll discover as you get higher up in both math and chemistry, the littlest details make all the difference. And if you forget a bracket, it does mean it's wrong. Close does not count in chemistry. Oh wait, one last one here. Iron 3 nitrate. So this kind of puts a few things together. I have a Roman numeral here. So what is iron symbol? Fe. Now, normally Fe, if you were looking at charges, Fe could be either a 2 or a 3. But I know which one it is now, because the Roman numeral told me that it's the 3 version. Anybody know what a nitrate is? Find it up there in that little box. Not NO. NO3 is the nitrate. Sorry if it's blurry. Nitrate should be NO3 minus, and nitrite is NO2 minus. They are very similar words. Only one is an ATE and one is an ITE. The charge on this guy then is -1. So how do I reconcile it so it fits? How many nitrates do you need?
3.
So I put a 3 right there with a bracket, yeah. Because otherwise it looks like I need 33 oxygens. That's not what I want. So what this means is we need 1 iron, and we need 3 of what's called a polyatomic nitrate molecule. So if I were to ask you how many individual atoms there are, if we were to like draw this, you'd actually have like 1 iron, little guy like this, and it would be surrounded by like 1 nitrogen, which would be surrounded by like say 3 oxygens, a second nitrogen, which is surrounded by 3 oxygens, and a third nitrogen, which is surrounded by 3 oxygens. How many oxygens are there total then? Yeah, 9. There's 1, 2, 3 for that nitrate, 1, 2, 3 for that nitrate, 1, 2, 3 for that nitrate. There's 9 oxygens. And that's because this 3 and this 3, they're kind of timesing together to be 9. Does that make sense? Cool. Okay. Do you guys have this slide, or was that the last one you had? That was the last one, or this one is? Okay, so here's what I want to do. I want to give you guys a 5-minute break because we've been sitting here for a while. When you come back, just like when you started class, here's a whole bunch of chemicals to practice naming. Okay? What I'd like to do is try these until maybe about, let's say about 1:45, and then we'll finish class by going over these. If you don't know what you're doing, call me over, okay? Please don't hesitate to ask me questions. That's why I'm here. But take a 5-minute break first.